Okay, so we're doing electromagnetic induction today. Okay, and like I said, this is one chapter you want to try and understand. Lots of application behind this. Okay, so let's. I'm going to go all over on the slides. Okay, just to make sure we understand. Okay, so here are the Maxwell's equations that summarize all electromagnetic phenomenon. This is the equation that we are studying today, the effect of this equation. Okay, and these are the causes, these are the effects. So what do you think this is saying?
How the magnetic field changes over time.
Okay, what this is saying is if you have a time varying magnetic field, if this is non-zero, it will produce an electric field. That's what it's saying. Okay, and I'll show you a thing. Okay, so how do we, so what you want to do is change the magnetic field at a given location. So let's do the following. We'll grab hold of a magnet. Yeah. As you know, a magnet produces a magnetic field. The field lines are like that. Okay, so it produces a magnetic field. And what we'll do is we'll jiggle the magnet. We'll oscillate it. Okay, so if you're standing here, when this comes closer, the magnetic field is getting stronger there, and when this magnet moves away, the magnetic field is getting weaker there. Okay, so what happens? That equation told us curl of E equal to minus del B by del T. Okay, so what happens is the following. You get an electric field as long as you're jiggling this magnet back and forth. An electric field is produced like this, and the electric field is in this direction. We'll learn about how to figure out the direction of the electric field and all that. So the electric field is tangent to that. All right, again, let's so if this were a magnet, if I jiggle this magnet right here, the electric field, there's an electric field produced like that. The further out you are, the weaker it is. And this electric field is produced at the speed of light. Okay, big deal. What do? What can you do?
Wireless charging.
So, if you have a wire there, it'll drive a current through it. What happened? I had to do work here. The work I did got converted to electrical energy. Did you guys understand that? That's the principle we're studying. That's electromagnetic induction. You induced an electric field. Okay, so let me show you. Oops. Like I said, this is the chapter you want to understand. So here we go. We jiggle this magnet. Right now, this is just being brought forward, and it'll induce an electric field in this region. And if you place a wire, you can drive a current in this wire without any batteries. So when this thing is not moving, there's no current. When you change the magnetic field, an electric field is induced, and you're inducing a current. Mm-hmm.
So does it still have that same magnetic field around it like a normal magnet would, or is it changing that magnetic field to make it circular above it?
Yeah, well, if the magnetic field was 0.1 Tesla here, when you move it closer, it changed to 0.2 Tesla.
Not like the magnitude of it necessarily, but the actual shape of it.
Yeah.
Okay.
Yeah, the direction will also change.
Okay. So instead of just being like that, it's just circular as it's moving. I think I'm explaining that.
No, This is an electric field that I'm drawing. This is not the magnetic field.
So there's, okay, I understand that.
This is the magnetic field.
But it creates the electric field above it in that.
Changing magnetic field creates the electric field.
Got it. Thank you.
That's what this equation is telling you. See? The equations have all the secrets to the universe. If this were zero, if the magnetic field didn't change with time, and that was this situation, if you held the magnet steady, the magnetic field around in this region is not changing with time. When you did this, you made the magnetic field change with time. And that induced electric fields, yep.
So it's like the moving charge creating the magnetic field is moving the charge in the wire?
No, it's, say that again. Say that again.
Oh, okay. So as you're moving it,
Mhm.
the magnetic field is created by moving charges.
Mm-hmm.
So those moving charges are making the charges in the wire start flowing, start moving, which creates an electric field.
Okay, I'll have to think about your remark. But right now, what we're saying is change. Okay, in this region, if you make the magnetic field change, if there's an existing magnetic field, if you make that magnetic field change with time, it induces this electric field. Okay. This changing magnetic field induces that electric field, yeah.
Is the electric field produced, is that,
And it will be produced as long as the magnetic field is changing. Soon as you stop this process, soon as you stop this, the electric field will go back to zero.
is the strength of electric field constant as long as you keep jiggling it?
At that location, yeah.
It
Well-
doesn't vary at all.
Well, I mean,
It doesn't vary with the frequency of the jiggling.
Or if the magnet's further underneath.
well, the electric field strength, it's instantaneously depending on the rate of change of magnetic field. So if you're oscillating, the rate of change of magnetic field is an oscillatory function. Okay. So this is what you want to. This is the statement you want to remember. Changing B induce E, and there's a whole bunch of applications based on that. Yeah. So we'll talk about this. Yeah. So okay. Right. So as long as you're changing magnetic field, you can induce an electric field, and you stick a wire there, you'll have a current flowing in this wire. You're doing the same thing here. What is this? A current is passing through this coil. Current carrying coil. A current carrying coil behaves like a magnet, remember? Your fingers are pointing in this way. This is behaving like a magnet, like that, okay? So all you're doing is you just replace this magnet with this electromagnet, that's all. And you're inducing a current. Okay. What happened here is you close the switch, the current went from zero to a finite value over a period of time. And as the current was increasing, the magnetic field was changing. So as long as the current was building up, till that time, you have an induced current. Okay. All right. Like I said, I'll sequentially go on the slides in a little bit. But for now, I'm going to go all over the place. Okay. Okay. So I just want you guys to physically understand this. Okay, we'll define something called magnetic flux. Magnetic flux is, so this is a magnetic field. Magnetic flux just measures, loosely speaking, how many lines go, magnetic field lines thread this area. Okay? How many magnetic field lines are threading this area? Zero. Okay? So this is how magnetic flux is defined, B dot A, okay, where A is the area vector. Okay, going back to this is, so when the magnetic field change, when you make it oscillate, there was an electric field like this. Line integral of this electric field is the EMF. That is the voltage that was induced. So you put a wire, higher the voltage, greater the current. Okay? So here is Faraday's law. The EMF, okay, the EMF induced in this coil is rate of change of magnetic flux. Okay? So, and we'll talk about the negative sign later, but don't worry about it right now. So the EMF induced is equal to rate of change of magnetic flux. And you saw the magnetic flux was B times A times cosine theta. Okay. So A, B, there's theta, or in this diagram it's indicated as phi. So the magnetic flux was, okay, so I'll write the Faraday's law. Induced EMF is minus d by dt of B A cosine theta. So imagine this was a loop of wire. This was it. So you want to induce a voltage in this loop of wire. All you have to do is make sure that this quantity changes with time. You guys following me? So this is extremely important. Here's $1 trillion. Literally trillions of dollars. Okay, to induce an EMF in this wire, voltage in this wire, all you have to do is make sure that this is non-zero. You could make B change, or you could have a uniform B. You could make area change. You could have somebody sit there and squish the piece of wire. Not practical. Or you could change theta. Somebody turn that wire. And you get the voltage in that loop of wire. All right, so let's look at that. All right, so there is that magnetic field. There is that loop of wire area. There is the angle theta. The EMF induced in that wire is minus d by dt B area cosine theta. Area A is the area of the loop. B is the magnetic field produced by these magnets. And theta is that angle. We're not going to change B. The magnetic field strength is constant. We're not going to change the area of the loop. All we're going to do is change this angle theta. How are we going to change this area? How are we going to change this angle? In a windmill, the wind is going to turn those blades. That's turning that loop. In a coal power plant,
It's cold to heat the water.
you boil water, the steam is turning that thing. In a nuclear power plant, you split nuclei, boil water, the steam is turning. In a dam, you store water behind the walls, let it flow, the flowing water is turning that thing. Okay. In a generator, you burn diesel. The diesel motor is turning that wire to produce electricity. So trillions of dollars are invested in turning that wire. Okay. In a natural gas plant, you're doing the same thing. Okay. So that's how we've been producing electricity. Now, in the last 20, 30 years, we've learned to produce electricity a different way, photovoltaic cells, but that's a different technology. Okay. But in this technology, we've invested trillions of dollars. Okay, so the EMF induced has, if you connect this wire to the outside like that, what you get is an AC voltage like this. Okay. And what this expression is telling you is that the voltage is a sinusoidal voltage, the amplitude is that, and in this expression, N is the number of turns of coil, A is the area of the coil, B is the magnetic field strength, omega is the angular speed at which it's rotating, okay? And so that's the frequency, okay? Now, so in all these windmills and all, the wind speed varies, and the frequency at which, using gears and all, what they want to do is have this thing rotate, have the wire rotate between 1,500 and 1,800 times a second, okay? But eventually they have to turn it into, so they turn it into DC and then back to AC with a frequency of 60 hertz. That's what you're getting out of the wall. So there's some processing that goes on. All right. Do you guys have any questions at this time? Okay. So the punchline is changing magnetic fields induce electric fields. Okay. So in this case, you might say that the magnetic field was not changing. You were changing theta, but if you look at it from the perspective of, if you're sitting on the coil of wire, you're turning, what you're seeing is the magnet is turning, and that's relative to you, the magnetic field is changing. Yeah. So you can think of it that way. Yep.
Why did sine omega go to 1 for Emax?
No, that's the amplitude. The amplitude is the maximum value this will have. That will be at sine 90, or sine n pi by 2, n plus 1 pi by 2.
Oh, okay.
And that'll be 1 or plus 1 or minus 1. This is just the amplitude.
Great. Okay.
Yeah. All right, so in any situation, if you make the magnetic field change, what can you do with the changing magnetic field? You can turn it into an electric field, you can turn it into electric current, and then with current you can do all kinds of stuff. Okay? So I'll show you an application. Okay? And then we'll get into the slides. All right, so here's a guitar string, okay? You make the guitar string vibrate. Okay, so let me show you. Here's a string. It's vibrating. Can you hear it? It's making sound. But why can't you hear it?
Other frequencies too.
Hmm? Okay, so what is it that you need? Huh? No, this is making sound.
You need a higher frequency.
No. You need to amplify it. Cool, huh? So in acoustic guitar, that sound box is the amplifier. Play an acoustic guitar and make 100,000 people happy in a stadium. You can't do that. So how do you fix that?
An amplifier.
So here's what you do. Now you know Faraday's law. So here's the string, magnetize the string. the string vibrates, the magnetic field is changing. Stick a coil there. You're inducing electricity. You're turning this vibration into an electrical signal. This you send to an amplifier. And then you can keep 100,000 people happy. Okay? Again, whatever vibration, you turned it into an electrical signal. Okay? All right, so here's another application that's in your bathrooms. What does this do? Okay, so let's say you're using a hair dryer, and if this wire broke and it hit the housing, then you're holding on to the housing, and current will flow through you to the ground, and you don't like that. Okay. All right. So how do we prevent accidents like that happening? I'm sorry? So this is called a ground fault interrupter, and here's how it works. Okay, so you saw a current produces a magnetic field, right? All right, so if the current is flowing this way, the magnetic field is like that, and so on. So here's current coming in, that is producing a magnetic field like that. And if the equal current is flowing out, there's a magnetic field in the opposite direction, which is canceling it. Okay, so when everything is normal, the magnetic field through this thing is 0. Let's say if the current flowing out is not equal to the current flowing in. If the current somehow leaks out through you to the ground, then the current flowing out is not equal to current flowing in. Then suddenly there's a magnetic field. Soon as there's a magnetic field, you have a current in this pickup coil, and you switch on it. You turn off a circuit breaker. Okay, so the ground fault interrupter, it can trip a circuit breaker within milliseconds. So that's what it does. It protects your life, is what it does. And all right, so you guys understand what are we studying today? We're studying Faraday's law. Okay, we are studying this equation. Time varying magnetic fields producing electric fields. Okay, so you saw examples like this. You make this oscillate this magnet. In this region, the magnetic field is changing with time, and an electric field is induced, and if you stick this wire, you get a current in it. Okay? So in this chapter, we look at time varying magnetic fields producing electric fields. Okay? So curl of E equal to minus. Okay. That's what we're studying. Okay, so for instance, here's a current flowing through a solenoid that's producing a magnetic field, and if you change the current, this magnetic field changes, and that'll induce a current in the surrounding coil. So we define magnetic flux as the number of lines threading this area, and it's given by B dot A. Okay. So the magnetic flux is B times A times cosine theta. Here it's written phi. Okay, so B times A times cosine phi. Okay, so if this were a loop of wire, the voltage induced in this loop of wire will equal rate of change of this. And like I said, in practice, the easiest thing to change is the angle theta. Okay. Okay, so here's a way to change the area, but this is not a practical way. But while you change this area, you would induce a EMF in there. Okay. All right. right, so here you could, here they're showing how to change B. Okay. Flux can change with change in B area or theta. Okay. So when will the light bulb light up? When this thing moves, it'll light up. And what matters is relative motion, like I said. In that loop of wire, the magnet was stationary and you change the loop, so it's relative motion that matters. So you can move the loop and the bulb will light up. You could turn the loop like that. Okay, so here is the magnet. Let me have your phone. Oh, I have my own phone. So you could, if this was a loop of wire, you could turn it like that, okay, spin it like that, and that would do it too. Here we are changing the area. This one doesn't light up. Okay. How about here? So this current is producing a magnetic field like that. If you move it parallel to the wire, the total flux through this thing is not changing and you won't induce anything. If you move perpendicular, then the magnetic field is getting weaker, and so you'll induce a flux, and that'll induce a EMF in that loop. Now, I want to make this remark before we go any further. So by the way, when you are turning that piece of wire, you need energy to turn that. You have to do work to turn that piece of wire. You have to apply torque. The work you do is torque times angular speed. Okay, who is doing the work? The wind is doing the work in the windmill and all that. And that work done, that energy is converted to electrical energy. Remember, no free lunches. All you're doing is converting energy from one form to another. In a coal power plant, the energy was provided by burning the coal, and then the steam did the work. In a nuclear power plant, the energy was provided by splitting nuclei, and then the steam did the work of turning. Okay? All right. All right, Lenz's law tells you about that minus sign. Okay? And it's related to the line integral and all that, but we won't talk about that. All right, so here is the magnet. As you move the magnet towards this loop of wire, the current induced in this direction. Okay, all right, and that's what this equation tells you. Okay, when the current is induced in this direction, remember this acts like an electromagnet, and stick your fingers out like that, your thumb points in the direction like this, and this electromagnet is acting like a magnet with the north pole facing like that. So what is happening? This is the guy that is producing this in current. And what is this current doing? It's opposing this guy. So the induced current is in a direction in such that it's opposing what is producing it. Okay. The induced current is such that it's opposing what is producing it. This is the classic example of biting the hand that feeds you. So it's a law of nature. And that's what the negative sign is about. Okay? So the polarity of the induced EMF is such that it opposes the change in flux that produces it. Okay, so here's a related phenomenon, motional EMF. Okay, So in this diagram, there's magnetic fields into the sheet of paper. And what you can do is you take a metal rod. What is a metal rod? What's special about a metal rod?
Has a lot of free charges.
It's got a lot of free charges. Okay? So you take a metal rod and you move it in this direction. Okay? And so let's look at a positive charge. The positive charge has a velocity in this direction. There's a magnetic field like that. V cross B, the positive charge will feel a force in this direction. So positive charges would collect this way. The force on the negative charge would be like that. Okay? And so you have a collection of charges. So you grab hold of a piece of metal and move it in a magnetic field. It's starting to act like a battery. Okay? How much charge will collect till the magnetic force on it is balanced by the electrostatic force. See, the negative charges are pulling on them. Okay? Anyway, the induced EMF or the voltage in the metal rod is B, the magnetic field, times the length of the rod in the magnetic field. That's what matters. Times its speed. Yeah, V is the velocity. Okay, and this is when the velocity is what matters is the perpendicular velocity. So if the magnetic field is like this in this room, the magnetic field is like that. I take this rod and move it parallel to the magnetic field, no battery. You have to move it perpendicular to, okay? So that velocity is perpendicular to the magnetic field. So that's the battery. And that's the voltage that's induced. And you can connect a bulb to this battery and you can light up the bulb. Yeah. Right. So here's a setup. There's the magnetic field, and you can apply a force and move this rod. It turns out that once you have a current flowing through it, the magnetic field will exert a force in the opposite direction. So you have to apply a force to keep it moving. So all this device is doing is, again, converting the work you did into electrical energy. That's what it's doing. Okay, what did I do here? I did work on this object and I lifted it. What did I do?
Gave it potential energy.
The work got turned into potential energy. Okay? In this case, the work I did got converted to electrical energy. And if that was a light bulb, it got converted to light. If that was a pizza, your pizza got cooked. All right, so again, you can look at it this way. When you move this guy to the right, the flux through this thing is changing. The flux is increasing because the area of this loop is increasing. Okay? And the induced EMF is equal to that. Okay, this is the rate at which you're doing work. Applied force times the velocity. Okay. And the magnetic force when current flows on this is given by that, and that is equal to this. So the work you did, all this thing is telling you is the work you did got converted to electrical. And the rate at which you did work got converted to electrical energy. So the power you exerted got converted to electrical power. So what is this device? Just a transformer. It's converting your mechanical energy into electrical energy. So work done by the applied force is converted to electrical energy. Okay, so we'll figure out, let's make sure we know how to figure out, and when we do problems, you'll do this. Induced current is, let's figure out the direction of the induced current, okay? So when you move it to the right, what is happening? Flux is increasing in that direction, in that direction in the circuit. So the induced current should be such that it opposes it. And if you have a current in this direction, the flux magnetic field will be coming out, and you're opposing the increase in flux in that direction. Okay. So when you move the rod that way, the induced current is this way. And if you move the rod this way, the induced current is that way. All right, so we said that if you take a metal rod and move it perpendicular to a magnetic field, you will induce a voltage like this. Okay. So they wanted to test it out. I mean, this was a sort of a fun experiment. They tested it using the space shuttle. Okay, so they tethered a satellite. This is 20 kilometers. 20 kilometers is from here to Edgewater. Okay. So they tethered this cable, and it's going through the Earth's magnetic field. Okay. So the voltage induced should have been 8,000 volts, and they observed about half of that, and charges were leaking away in the ionosphere. Okay. So it's interesting enough for them to test it out there. Okay. Okay, so here's a bunch of charges that are at rest. What do?
Produce electric field.
They produce electric field. Okay. So let's say here's the electric field in this region. Now it turns out that for this electric field, if you take a line integral of this electric field around any loop, you get 0. Okay. This electric field is called a conservative electric field. When you produce an electric field by changing magnetic fields, this electric field, see, this line integral is not 0. The line integral is the EMF induced. So this is a non-conservative electric field. So the electric field produced by changing magnetic fields, has a different nature than the electric field produced by static charges. Okay? Just a fact. So this is an AC generator. Like I said, it's converting one form of energy into what kind of energy?
Electrical.
Yeah, it's converting to electrical. So it should really be called a transformer. And generator is sort of a bad name, but anyway, that's what we're going to stick with. Right. So if you connect this loop of wire to the outside with brushes like that, you get an AC voltage. Okay. There's the amplitude of the voltage. Okay. N is the number of coils, and GE made a lot of their money doing this, but now they're doing all kinds of other stuff. A is the area, B is the magnetic field, and omega is the rate at which it's spinning. If you connect this wire via brushes to the outside like this, then you're converting it, you're producing a DC voltage. Okay. So this is sort of a fun toy. You have a battery and this loop of wire. When you close the switch, as the current builds up on this, it produces a magnetic field. And as the current is building up, this magnetic field is building up, it's changing. And if you have a metal ring like that, while the magnetic field is changing briefly, you will induce a current in this ring. And in the opposite sense, if that's a north pole and this will a north pole, and this will repel it, and that ring will fly off. With some setups, you can have the ring fly in, you could do it in that stairwell, and the ring would fly all the way to the ceiling. Okay. You learned about ground fault interrupters. Okay, so these devices can switch off if you have unequal currents flowing. It can trip a circuit breaker within milliseconds. Okay, so that's what that is. Okay.
So that's GFI, what's a GFCI?
Now, with some kind of enhancement to it. I don't know what the C stands
What if it's current?
for. ChatGPT. And then I can try and explain it.
Ground fault circuit interrupter.
Yeah, there you go.
Just the
So, same thing. All right, so now you know how to turn these vibrations of the string that you couldn't hear into something that 100,000 people could hear. Yeah. Okay, again, changing magnetic fields can be turned into an electrical signal, and once you turn it into an electrical signal, then you can do anything you want. Okay. So let's say if this magnet wasn't there, here's a simple pendulum. Okay, or you have a metal thing, and you could set it in motion and it would swing forever. You bring this magnet in, as this metal goes through, what happens is this changing magnetic field, as it's going through, the magnetic field is changing, and the induced current will be such that this will become a north pole, and that's repelling it, it's slowing it down. And once it goes past, that'll become a south pole, and it's pulling it back. So this is providing friction, and this will stop very fast. Big deal. Why do you care? Here, you could use that to brake. Okay? So what you do is you can have a coil like that hanging near the train tracks. When you want to stop the train, all you do is flip a switch, pass a current through this thing. This is producing a magnetic field, and that will induce a current in the tracks such that it will stop this train very fast. Okay, so if you're holding it there and the train is going in this direction, this induced current is a south pole pushing the train back. This is a north pole pulling the train back. And you will get a very smooth and fast stop without any jerks. You won't even spill your hot coffee. Why is this useful? Do you guys know what is the cheapest mode of transportation? Huh?
Walking.
Yeah, walking. Yeah, but if I want to, but Amazon is not going to hire you to transport its stuff while you're walking. All right, so it's, but you guys were right. Water is the cheapest, and then train, and then road. I think train transports per pound per mile 5 to 10 times cheaper than a truck. So why do you see semis on the road, and why is not everything being transported by train?
Is it slow?
What?
Because they're going certain routes, right?
Time is worth money. If Winnie's stuff doesn't come by tomorrow, she gets upset. She can't wait for a week. Time is money. So that's why you're willing to pay more. Okay? But anyway, you could pack more trains on the line if they use electromagnetic braking, because you have a short braking. Yeah, so if the Congress would pass this law, then you would be good. So here's how metal detectors work. If there's no metal, what they do is they send an AC, they have an AC coil here which is producing a magnetic field that is changing, that's inducing a current in this receiving coil. Soon as a piece of metal intervenes, the magnetic field is in the opposite direction. The magnetic field the receiving coil is receiving is reduced. The induced current in this thing is reduced. Okay. So that's how that thing works.